See? You can do it. I knew it. I knew you could do it. I will begin with a word of prayer. Dear Father, we thank you for this day. I thank you for the students. Just ask you to bless this class today, Lord. Help us to use the time wisely, Lord, since we have less of it. Amen. All right, so let me get right into it. This is Theorem. And I think there's some unfortunate, well, I don't know if it's really, not really typos as much as they are unfortunate confluences of notation. So I'll try to fix that here in my proof. This is holomorphic for z minus z naught less than or equal to r. And suppose that this sequence of functions converges uniformly to, let's say, f, all right, for the disk centered at z naught with radius r, which is z meeting that condition, all right. Then for each, hopefully I won't drop my computer. Oh, this is kind of a workout, r less than r. And each m greater than or equal to 1, the sequence of mth derivatives converges uniformly to the mth derivative of the limit function for the disk, well, for z in the disk centered at z naught of radius little r. All right, so this is the theorem. Let me try to draw a picture of what's going on here. There's two different r's in this theorem. There's the one r, right, like this one. And so that is the disk on which we're given that the function is holomorphic and uniformly convergent to f. All right? And then we're looking at a subdisk of that, of radius little r, which I'll make purple. Okay? So this one has radius little r. All right? And the claim is on that subdisk. In fact, for each subdisk, all right, you notice this right here, right? We have that the sequence of mth derivatives converges to the mth derivative of the sequence of the limit function, and uniformly so. All right, so the idea of the proof is basically to say, okay, well, if this is less than that, then this is like a common trick to play when you're proving things like this, is we put another circle in here. All right, and that one's going to have radius s. So what we have here is r less than s less than big R. All right, that's the choice of r and s and r. And so then what we're going to do is we're going to apply the Cauchy integral formula for the mth derivative of, well, let's do it. Apply Cauchy integral formula on fj of z minus f of z, and not just that, but the mth derivatives of those. All right. And that will give us m factorial divided by 2 pi I integral. And so the question is, I'm applying the Cauchy integral formula on the disk of, well, let's see here, the circle centered at z naught circle of radius s centered at z naught. All right. So that circle, which is, by the way, the boundary of the disk of radius s centered at z naught. Okay. So apply Cauchy's integral theorem to the green curve, and we're doing it for z. This z is actually fixed. All right. So Cauchy's integral theorem gives me fj of w minus f of w divided by w minus z, I suppose, to the m plus 1th, if I remember right, dz, or excuse me, dw. All right, so using w as the integration variable. So I'm noticing that the difference, so how am I doing this? How do I know, we have an earlier theorem, right, that the mth derivative of a holomorphic function is once more what? Holomorphic, right? And so we have that theorem to work with. I'm using that. And so I know that this is a holomorphic function. In fact, this is a holomorphic function on the disk. Actually, on the bigger disk, right? We actually have that's holomorphic on the red disk, but it's certainly holomorphic on the green disk as well, right? So I'm using that there. This z, though, let's be careful. Where is z? Z is a fixed point, and we want it to be actually inside the purple circle. So z is like in here. Okay, so this is, so here, z is an element of the disk of radius r, centered at z naught. So we have that the modulus of z minus z naught is less than r, right? And what else do we know for that integral? Whereas for the integral above, if we have w in the circle of radius s centered at z naught, has modulus of w minus z naught equal to s, right? This is by construction. So then we can look at this pretty neat modulus w minus z modulus, all right? So what's that going to be? So I could draw it in the picture over there, but I'll just add. So this is really w minus z naught, right? Minus z naught. Do you see that? So I just added and subtracted z naught, right? And the reason is then I can do that. This is greater than or equal to the modulus of w minus z naught minus the modulus of z minus z naught, right? Because the modulus of the difference of two complex numbers is greater than the modulus of the difference of the moduli of those complex numbers. This is something you should try to hardwire into your brain for the sake of analysis in here, right? This is kind of a close cousin to the triangle inequality, but it's the inequality goes the other way, right? Okay, and then what's that? Well, this is S, right? And this is what? This is at most R, right? Well, it's at most almost R, right? So what can you say about that difference? It's greater than or equal to what? Greater than or equal to S minus R, right? So, consequently, as, you know, Fj converges uniformly, we have that there exists a, we can look at Fj of w minus f of w, right? That modulus is less than or equal to epsilon sub j, which goes to 0 as j goes to infinity for w in the circle, right? I mean, we have uniform convergence of the sequence on the whole red disk. We certainly have uniform convergence on that circle, right? So we have this best case estimator, but we can do more, right? So we got the f j of w minus f of w divided by w minus z to the m plus 1. So let's use what we just figured out. What's that less than or equal to? Well, it's less than or equal to epsilon sub j, right? Divided by, apparently, s minus r modulus, well, absolute value in this case, to the m plus 1. So we've got this wonderful bound on the integrand that we got from the Cauchy integral formula. And let's see here, let's put it together. So this implies then that the modulus of the jth derivative of m of z minus the mth derivative of the limit function at z is less than or equal to m factorial, right? M factorial divided by 2 pi. I kept the I in my notes, you know, and I shortly thereafter make a comment that there's some errors in Gamelin that have been corrected in the above, right? Like, that's not one of them, though. So I kept the I in the inequality, which is not good, right? You take the, we're using the ML theorem on, let me call it star. So use the ML theorem on star. So I keep the m factorial over 2 pi. I've just shown that the integrand here is bounded by epsilon sub j over modulus of s minus r to the m plus 1, right? So what you do, and then ML theorem, what's the length? What am I missing? What's the length of, by ML theorem? Two pi what? 2 pi s, right. So what happens as j goes to infinity here? S minus r is a fixed number that describes the, you know, how much bigger the S disk is from the R disk. That's fixed, finite, whatever. And as j goes to infinity, m is fixed here as well, right? This goes to 0. So you can call this whole thing, let's say, rho sub j, and see that rho sub j serves as a best case, or worst case, I forget what my terminology was. It proves uniform convergence, right? It proves the uniform convergence of the mth derivative sequence on this on this closed subdisk of radius r. Does that make sense? Trust me, this is a considerable clarification of what's currently in the notes, because the notes, I don't use the notation disk and circle. I have inequalities that are like in the notes at the moment. Instead of writing this, I just wrote modulus of z minus z naught equals to s. And okay, technically that's a good description of it, but at least I probably should, instead of writing that, I should probably have written this at a minimum instead of that, you know, because w is the integration variable. So if I'm going to describe the curve in terms of the integration variable, it'd probably be good to use the integration variable as opposed to z, which has a fixed but different meaning in the proof. Z is this fixed point back in here. It took me about a half hour to like clarify the use of w and z in this theorem. So what I've written on the board I think is clear. So anyway, I'm going to go on. But this is pretty nice because now we have a proof that the, well, you guys caught up with me? I see you're still writing. Are you? Okay. Can I put the... So I wanted to write that out. And I probably should write out the next thing as well. Come on. So a sequence of holomorphic functions on a domain converges normally to an analytic function f on the domain if it converges. What's going on here? Okay. Oh, there it is. Oh, you don't have to zoom out. I'll come back and do it in a second here. So this is the definition of normal convergence. So a sequence of functions is said to converge normally to an analytic function on a domain if it converges uniformly on each closed disk inside the domain. Remember, a domain is open, so normal convergence is meaning that it uniformly converges on every like subdisk of that. All right. Now and that's what we just proved. We just proved this theorem that, you know, if we have this condition, then we get normal convergence of the mth derivative of the sequence. If we have normal convergence of the function. This term was actually introduced by Baer of the Baer category theorem in, when was it? I've got the quote here. It's kind of funny. 1908. Anyway, I have blathered on too much about less interesting things today. I cannot afford to read that quote. So what's a power series? A power series, I'm being careful to be below the board, so we should be on the camera, right? Oh, you moved it up? Is it like, where's the top of the camera? Is it here? Above the heading? Okay, that's fine. A power series centered at z0 is a series of the form sum k equals 0 to infinity a sub k z minus z0 to the k, where of course we assume that the center of the series z0 and the coefficients a sub k are complex numbers, all right? So this is not surprising, is it? Right? And the central thing that will make all of the proofs from here on out in this section work is Abel's convergence lemma. All right, so let's just take a minute here to try to prove that. Here's Abel's convergence lemma. It says, suppose for the power series, suppose for this series, right, suppose, so you can pan over here, Sam, ak z to the k, there exist positive numbers s and m such that the modulus of a sub k, all right, times s to the power k is less than or equal to m for all k. All right? Then this power series is normally convergent for what? For the disk of radius s. So z and c such that modulus of z is less than s. So just to draw a picture again, what this is saying is that we've got this disk of radius s, and we've got normal convergence on any we have uniform convergence of the series of functions on any closed subdisk. All right? So, like this one. This is Abel's convergence lemma. So let's look at the proof of that. The proof is kind of similar to the thing we were just doing, in the sense that it also involves the r and the s in some sense, because we have 0, less than r, less than s, all right? And we're going to set q equals to r over s. What can you say about that? R over s is what? It's less than 1, isn't it? And then we're going to observe for z in the, modulus of z less than s. Oh, wait a minute. No, not s, but what? R. For modulus of z less than r, we have the following. We have that the norm, the modulus rather, a sub k, which is the norm, so I guess I wasn't wrong, but all right. Absolute value of a sub k times z to the k is less than, can you just pick a term already? All right, modulus of a sub k r to the power k, all right, which is equal to a sub k times s to the k times r over s to the k. So I just divided and multiplied by s to the power k, which is useful to me because now I have the modulus of a sub k times s to the power k times, well, q to the k in my language. Oh, and then I guess I said, all right, so wait a minute. Oh, idiot. Wait a minute, no. How do I know? I'm sorry, how did I replace that with m there? Oh, yeah. Thank you, Bethany. What are you telling me? Yeah, I mean, that's an assumption of the theorem, right? So I can't just derive that this is less than m, right? That's true. That's data that needs to be given to us. That's a precondition of the theorem. I better not be able to derive it. If I could derive that, that would be weird. So this is assumed to be less than m, which is just peachy because, well, now by Weierstrass's m-test, we have normal convergence. Uniform convergence, rather, on this disk. See, because this, if you take the sum, k equals 0 to infinity, right, of m q to the k, what you got? You've got m over 1 minus q by the geometric series result, right? This is a convergent series. In other words, this series, m times q to the k, serves as a majorant for the given series, a k z to the power k. So by Weierstrass's m-test, we have uniform convergence for all z for which this estimate makes sense. Which z are those? Well, any z less than r, right? So we've just proved uniform convergence on the closed subdisk of radius r, which is what we set out to do. Since r is arbitrary, this gives us normal convergence. Does that make sense? So by Weierstrass m-test, we're done. All right. Well, this is pretty neat because this leads us to the following insight. Oh, come on. Let's see here. There we go. Am I? There we go. Sam is really selling not knowing how to use a camera. I don't buy it for a second. I mean, I don't know what to zoom in and zoom out. I've brought technical LaTeX issues to you, and now you don't know zoom on a camera. It doesn't track. It doesn't track. I'm not buying this. I do like it, though. It reminds me this morning, I was about to leave for work, and I couldn't find my watch. It's like, where's my watch? What's going on? I'm looking, I'm turning over couch cushions, moving my chair, because I left it beside where I was earlier. And I was like, what is going on? I can't find it. I told Jenny, I'm like, where's my watch? Where's my watch? And so I'm just turning the house. I'm going upstairs and downstairs, looking everywhere. Finally, Jenny's like, all right, whichever child can find the watch first gets $1. As soon as she says that, Matthew pulls his hand out and goes, Because she did this before. She offered $1 for something somebody could find. So he had taken the initiative of hiding the watch to make $1. Now, I personally thought this was hilarious, but my wife did not. There was so this is kind of like Sam with the camera. Okay, so the corollary, I tease because I love. Corollary 10.4.4, it says this: if the series converges at z not equal to 0, then it converges normally in the open disk of that radius. In other words, if you have one point of convergence, you're guaranteed convergence within the disk that defines that from the center. You can't have the situation where your power series converges at 3, and yet somehow there's a point like distance 2 away from the center where it diverges, right? Convergence is contagious. As soon as you have one point of convergence, you get a whole disk of convergence. And the proof is pretty simple. Here it is. If this converges, right, that means by the kth term test that must go to 0 as k goes to infinity. But that gives us that the modulus of that times z naught to the k goes to 0 as k goes to infinity. So we can use Abel's convergence lemma and look in this and go, we got the modulus a to k, right? And here's my s to the k. My s, quote unquote, is the modulus of z naught, right? This is a sequence of positive terms. And by the way, this is a convergent sequence of positive terms, which means it's bounded. So that gets me the m, right? And so there we go. We've got, I shouldn't do that. The modulus of a sub k times z naught to the k less than or equal to m for all k. Sorry, I mean, the s, I didn't write it explicitly, but I really should write, modulus of z naught equals to s is the idea here, okay? This proof would be improved by me writing that. Sorry about that. Now, on the other hand, if we have a point of divergence, then what? That doesn't necessarily mean that, it diverges everywhere inside either, right? I mean, we know if we have a point of divergence, then we're going to diverge outside that, right? Because if we had even one point of convergence outside a given point, then this theorem says that it converges inside that point of that radius of convergence, right? So divergence at one point does imply divergence outside that distance from the center, but we don't know what happens inside. This leads us to make the following definition. The radius of convergence for a power series is said to be r if the series converges for z less than distance r from the center, but it diverges for distance r beyond distance r away from the center, right? And the theorems we just proved, admittedly for z not equal, the theorems we just looked at were for z not equal to 0, right? But you could easily see that the two things I just proved for you, we could easily do those same proofs instead of being centered at 0, center them at z naught, right? It would have cluttered my arguments a little bit, that's why I didn't do it. But you could easily go back to the previous two results and do them for z minus z naught to the k rather than z to the k. Do you agree? Hope you agree. All right, so so this is the radius of convergence, and now it actually means what we say, right? Because in calculus 2, we talked about the radius of convergence, but radius of what disk, right? It's an interval, but now the radius of convergence actually is the honest to goodness radius of a disk. So the terminology has come well full circle. Anyway, we can also have the radius to be infinity if it converges everywhere. Such a series, of course, is said to be entire, or just 0 when it just converges at the center point. Yes, sir?
What happens with the stuff on the circle?
On the circle, anything can happen. So I guess the circle is kind of like Vegas or something. I don't know. Oh no, now I'm gonna have to edit it if I'm not careful. All right, moving on. Let this be a power series. So we have a power series, right? And then there is a radius, either 0 or infinity or something finite, such that the power series converges normally on the disk of convergence. And it does not converge if we're outside that disk. All right? So in other words, the radius of convergence is just what it sounds like, but it's a little bit more than that, because it really should be the radius of normal convergence. Because we don't just get plain old pointwise convergence of a power series. We actually get uniform convergence on any closed subdisk of the disk of convergence. And here's the proof. We just define R to be the supremum of the real numbers t, such that this is a bounded sequence. Right? Whatever that supremum works out to be, by Abel's convergence lemma, we can prove that this series converges normally inside that disk. All right? That's pretty much it. I will break from my inattention to acalculus momentarily. When you study power series over an algebra, it's so much worse. When we study power series over an algebra, there's these weird things that happen with zero divisors. I found series over algebras which converge on like an open, instead of disk, open square. They actually converge on like a square or a diamond. And then they have like hairs of convergence out to infinity. Or just one, actually. I'm not sure you can have two hairs of convergence. So like the structure of the set of convergence for a power series over an algebra can be much weirder. So complex, on the other hand, single variable complex theory, the domains of convergence for power series are just nice, simple disks. This is one of the things that gets more complicated when you study several complex variables. The domains of convergence for multivariate complex series are more complicated as well. It's one of the main interesting features of several complex variables, which I don't have much to say about because I'm not an expert there. And that stuff gets deep really fast. All right, so we can go back to some of our previous examples, of course. The geometric series, we've shown that converges on the open unit disk. In fact, we have normal convergence here, which means we have uniform convergence on any closed subdisk, right? We do not have uniform convergence of the geometric series on the entire disk, though, right? We've proved that you get that the convergence is not uniform if you go all the way to the edge. You have to look at a closed subdisk. It's picky, but true. Likewise, z to the k over k to the fourth, we can majorize by the p equals 4, if you like, series. And so we get uniform convergence on any closed subdisk. Again, normal convergence on the unit disk. Here's another one. It's got a little bit more computational flair to it. I'll go on. This one, these are just some examples, basically, just of convergence and divergence. This guy is one that has radius 0. If you look at this, this is going to diverge by the nth term, well, you might say kth term test, if z is not equal to 0. If z is not equal to 0, the kth term in the series here blows up. And this one, on the other hand, z to the k over k to the k, is very nice. Starting at k equals 1, that converges independent of what z is. So that's got a radius of infinity. All right, next theorem. This is the term-by-term calculus theorem. This simply says that if we have a power series with radius of convergence r, then we can obtain the derivatives by term differentiation. You remember this from calculus 2, right? For real series. Well, it's true here. And the difference is I will actually show you a proof of that. Okay? No one really proved that for you in calculus 2, unless you had calculus 2 with me. Did you have calculus 2 with me? No, even if you had calculus 2 with me, there's only one semester I actually proved it. To really prove the derivative of a series is the derivative of a series. There's two things you can do. Well, I'm going to shut up. It's uglier than you realize. And it took me about 5 times teaching Calc 2 before I even noticed it. No student ever pointed out to me. What we always do is we show you that if you differentiate a series term by term, that series converges. Well, that's lovely, all right? But that does not prove that that's the derivative of the original series. To prove it's the derivative of the original series, you must show that it satisfies the difference quotient, right? That it's actually the derivative. To give arguments which support the fact that the term-by-term derivative is actually satisfying the difference quotient for the derivative of the function defined by the series, that's actually kind of a pain. It's even more of a pain for algebraic series. I have a proof in a paper I wrote. But anyway, I digress. So get back to it. So here we go. We got this series. We're given it's normally convergent on the disk of radius r naught, right? So we have these. What's our kth term in the series? It's just power functions, right? We know power functions are holomorphic because you can differentiate these k-fold times, right? No mysteries there. Can you take the complex derivative of a constant times z minus z naught to an integer power? This we can do, right? This is definitely complex differentiable. And furthermore, the limit function, this guy right here, is holomorphic by a theorem we already proved. In fact, we know that the derivatives in the second and the third, and in fact the mth derivatives are holomorphic on this disk, right? By the theorem I proved at the start of today. And you can calculate the derivatives explicitly like so. So one of the things is, of course, if you evaluate evaluate at z naught the series, what do you get? You just get the constant term, right? Because these are all 0. If you evaluate the first derivative, the series of first derivatives, you just pick off a sub 1 and so forth and so on. In fact, so this is the formula for the kth derivative series. The series formed by kth derivatives would be given by this, right? We start from j equals to k. We've got these terms from the term-by-term differentiation, and that. So, of course, if you evaluate the above at z equals to z naught, we just pick off the constant term, which then gives us the formula a sub k is equal to f, the kth derivative at z naught divided by k factorial. All right, I'm sorry I'm glossing over this a little bit. To summarize the proof, it's really just this. The thing we did at the start of class shows that if we have a series, right? Well, we started class, we did a sequence of holomorphic functions, did we not? But remember, a series is what? It is the sequence of partial sums, right? And if you look at the partial sum of the power series, it's definitely what? A holomorphic function, right? Because it's a finite linear combination, finite complex linear combination of power functions, right? And each one of those is holomorphic. And so we know that if that converges to a holomorphic function, and we're assuming that at the start of this, then we know that its first derivative, its second derivative, its third derivative, its fourth derivative will likewise be holomorphic. And I'm talking about the sequence of partial sums. But then that being holomorphic implies that the series is holomorphic, as well as the fact that we get the term by term from the mechanics of the calculation. So it's really just combining what I did at the start of today with the idea that the series is convergent if it's uniformly convergent if its sequence of partial sums is uniformly convergent. Anyway, after all of that is done, what have we got? We have license to do term-by-term calculus on power series. So from here on out, most of the rest of this section is like calculus 2 examples, but with complex variables. So the first 2 examples I have for you are just algebraic, right? This one, you know what I do? I like pull out the z to the 4th, and then I've just got like a geometric series with radius z cubed. So I get z to the 4th, or 1 minus z to the 3k. Oh, come on! That is totally bogus. That's a z cubed. That k is not there. Okay? Nah, pun intended. Oh, it's also not here. Sadness. I'd blame the meeting, but I wrote this long before I went to that meeting. Another example, if we have the series z to the 2k plus z minus 1 to the 2k, we can write it as the sum of the two series, provided that these separately converge, right? And those are both geometric, and they give you this, and they give you that. Now, this converges to that, and that converges to that, given separate conditions on z. This one converges if the modulus of z is less than 1. This one converges if the modulus of z minus 1 is less than 1. So if you draw those, what's that look like? Z less than 1, modulus of z minus 1 less than 1 is like this, right? So this is where both of those calculations make sense. Is that a disk? Wait a minute. You mean to tell me this series is representing this function, but not on a disk, but on a whatever that is. In other words, this series converges there, I think. Well, that's a separate thing. Prove that the series only converges there. I think it only converges there, actually. Why does this not contradict what I just proved, that the power series has a disk of convergence? Right. So Sam has caught me. This is a sum of power functions, but this is not a power series. A power series has to have the form a sub k, z to the k. This matters. Not paying attention to that, like writing z, or if you change this multiplicative, like if you do z to the k times z minus 1 to the k, and try to analyze that, those things behave differently than power series. They're not power series. They have a really different structure, which nobody talks about. That's probably too strong. Somebody talks about it. Just not me. Here. Wait a minute, I already did. Oh well. Time travel back. Remove these comments. We can also do geometric series tricks, right? Like if you differentiate that, then, you know, on the one hand, I have that this is equal to that by the geometric series, but I can also differentiate term by term, and that gives me that the power series of this is that. So all those things we learned about differentiating and integrating geometric series in Calculus 2, or didn't learn, they all matter now. There's a few more examples of that here. Log z, log of 1 minus z, right? If we differentiate this, we get minus 1 over 1 minus z. I can geometric series that, right? And so that means that the derivative of the log has this as its power series. But if I integrate back, that gives me that log of 1 minus z is represented by this series. If you plug in z equals to 0, log of 1 is 0, right? Principal log of 1 is 0. And there you go. That's a power series representation for the principal logarithm. Well, not quite that. It's the log of 1 minus z I have right there. And then finally, the last two theorems here, which I'm sorry I'm shortchanging. If I maybe I'll have energy to do it next class. I got to think about it. But this theorem here, my biggest complaint about the notes right now. Oh, am I off the camera? No, I'm not. So my biggest two complaints about this theorem, the rest of the chapter, this section in the notes, is I failed to do something very important, which is to label this theorem. What is this theorem? The what? It is the ratio test. This says that if you look at the ratio of the coefficients and they have a limit, which is either finite or infinity, then the radius of the convergence is that limit. All right. And again, the proof is I think comparison test, and the proof is relatively straightforward actually, and maybe I should do that sometime. But we have a ratio test, and there's also a root test. If you take the kth root of the modulus of the series, if it has a limit as k goes to infinity, which is either finite or infinity, then the radius of convergence is actually given by the reciprocal of that root as k goes to infinity. There's a more delicate theorem called the Cauchy-Hadamard theorem, which replaces this with the limit superior, which is probably useful to know about if you go on, but probably won't matter to us. So we have a ratio test, we have a root test. They're similar to what you've already seen. And so I've asked you some questions in the homework about, convergence or divergence of given series. At the moment, you really have 4 things to work with. What are those 4 things? Let's review. We have the nth term test, always a go-to for divergence. We have the geometric series result, which is actually a whole family of results now that we have the term-by-term calculus theorem, right? Because we can integrate and differentiate that to get related convergence or divergence results. And then what else? We have the Weierstrass M test. That's very useful for getting uniform convergence, right? I've digressed now. I'm going to have 5. Then we have the ratio test, and finally the root test. And that's pretty much our arsenal to work with, all right? And that'll get us pretty far. So what's up next? Power series expansion of an analytic function. So let me contrast what we just did with what we're about to do. What we're about to do is take a given holomorphic function and find a power series which represents it. The previous section was about, here, you're given a power series. What is the structure that you're allowed? You can differentiate it. You got a disk of convergence. This next section asks a different question. Given a function, how do you find a power series to represent it? Which is a related but separate question. So anyway, we'll start there next time. Thanks, guys.